GastroPlus.com. Also, upon request, the presentation slides can be made available and shared with colleagues. It is now my pleasure to turn the presentation over to Viera. Viera?
Thank you, John. Good morning, good afternoon, everyone. Thank you all for taking the time out of your busy schedules to learn more about the recently released GastroPlus version 9.0. I'm sure many of you have already seen or heard some parts of what we will be discussing today, but I hope that everyone will also find something new and exciting as well. Even though there were a number of smaller modifications and features and so on, today's talk will really focus on the 6 major additions or changes in GastroPlus, and these would be the new modules for additional dosage routes and for biologics, the expansions in the admit predictor module. We've added some new DDI standard models, so I will talk a little bit about those. And some of you already noticed that we have changed the installation and licensing structure, so I'll make a few brief comments on that aspect as well. To get started with the modifications or expansions on the admit predictor module, one aspect that you will see, especially for those utilizing GastroPlus in the early discovery stages, you will be pleased to see that you can finally do a complete PK model setup during the structure import. So if you are importing a library of compounds, a number of different compounds, you no longer need to go subsequently into each of those created records to set up the PK model, create the clearance, and make all the subsequent modifications. You can now do all of those settings directly during the structural import in this setup window. You can start with selecting a PBPK model. This drop-down for the PK model selection will contain all of the available PBPK models. If you have not created physiology yet for the species or population that you are trying to model, you can always create it directly from this window. So everything is set up directly during the structure import. And you can also select a method for the KPs, for the tissue plasma partition coefficients that you would like to use to calculate for all of the newly imported compounds. So again, you would not longer have to go to each individual record and calculate the KPs. If you want to use a method different than default, you can do the setting directly here and have the complete distribution set up as a part of the structure import. Subsequently, you can also select the physiology for the intestinal physiology that you would like to have set up for all of the records. And here we've tried to do a little bit of a smart selection or smart pre-selection for you, where the intestinal physiology drop-down will contain only those physiologies which are relevant for the selected PBPK physiology. So the program will not allow you to link the PBPK human model with rat physiology or something like that. And this drop-down will contain not only the built-in physiologies, but also any user-defined physiologies that you may already have available within your GastroPlus or database directory. So again, a complete setup for the physiology is going to be possible. You can also define the renal clearance. And again, if you are setting up a PBPK model, you have the same options to calculate the renal clearance based on the physiology, the same options that you would be selecting in the kidney tissue if you are processing this one record at a time, the FUP times GFR fraction of kidney blood flow. But you also will have an option to select from one of the experimental values. If the file that you are importing with the structures contains experimental values for your renal clearance, that field will show up here as one of the possible selections, and you can import the experimental renal clearance as well for each of the records. So this will allow you, with the same set of predictions that you had before, already getting a more complete setup and this was really focused more on streamlining the use of Admit Predictor module and allow you to as much of it as possible on this window without having to do to each record separately and do individual settings. We did make also, and the just as a follow-up, when you do import the structure and you do your complete settings, your PBPK table can automatically contain the records for all of the imported structures with their calculated KPs, possible imported clearance, set up renal clearance, and so on. We did make modifications also to the predictive capabilities of this module. You may be aware of our Admit Predictor module, of our Admit Predictor software, containing models for predicting clearances for some of the CYP enzymes, predicting Km Vmax values or intrinsic clearance for those CYP enzymes. So with version 9.0, we have linked these predictions also directly to GastroPlus. So during structure import, you can select to have predictions of not only the basic physical properties as you had before, but also getting predictions for the metabolic clearance utilizing some of these models. Of course, it will require some of the additional licensing for that module. So for the models that we have available, Admit Predictor currently includes Km and Vmax or clearance models for 5 human CYP enzymes, 1A2, 2C9, 2C19, 2D6, and 3A4. For all 5 of these enzymes, we do have models based on in vitro measurements in recombinant enzymes. And for CYP3A4, we have also additional QSAR in silico model based on in vitro measurements in human liver microsomes. So within the Vmax, Km, or clearance selection dropdown, you have at least 2 options to use predicted clearances or predicted Km Vmax values based on all recombinant systems, including 3A4. Or you can use the predictions from 3A4 HLM and using the recombinant systems for all the other 4 enzymes. In addition to these enzyme-specific models for these 5 CYPs, we also have an overall microsomal clearance model. So when you are importing only the intrinsic clearance, you have an option for 1 more predictive model to get a total microsomal clearance prediction. So we do cover quite a bit of options for predicting microsomal clearance or predicting metabolic clearance, at least as it's relevant to the major CYP enzymes in the human. As you are importing these structures, of course, they need to be converted into the units that GastroPlus prefers to use for Km Vmax or for clearances, and the conversion is built in. Directly during the structure import, you can view all of the conversion parameters, the standard conversion parameters and conversion factors that you would be using even when you are importing or even when you are entering your in vitro clearances and using the metabolism converter. In addition, here you can specify into what enzyme, into what locations you want to add the enzyme if you are importing Km and Vmax values. And the defaults are preset to account for known expression levels in the gut. So as you can see, for some enzymes, we do not recommend placing the Km Vmax values into the intestine if it does not have a significant expression levels. For others, like 3A4, 2D6, we would be creating the 2D6 in the gut as well. And again, just like with other properties, you are not limited to just getting a predicted properties by our models. But again, if your SDF file or SMILES file or whatever file with the structures you are importing into the program contains a field with your experimental in vitro or even in vivo clearances, you can select that directly here in these drop downs, and instead of predictive models, you can import a experimental value directly. If you are importing experimental value, then you would be asked to also define the units in which your clearance is coming, in which your clearance was saved in that file. So again, the program can convert it utilizing the conversion factors into the units that GastroPlus requires for the in vivo simulations. And when you are importing the structure, so this would be at the end of the import, you would get not only the record set up for every compound that you imported, but also had the predictions for the K and Vmax values if you selected to import Km and Vmax, or simply have a clearance in the PBPK or in the drugs table if you choose to import only linear intrinsic clearance instead of K and Vmax values. Taking this a little bit further and streamlining it a little bit more even to the early predictions of drug-drug interactions, in the cases where you decide to import just a simple intrinsic clearance, which is not giving program information about which enzyme is responsible for that metabolism, but if you are importing the predicted values, the program knows how this clearance came about, which enzymes were contributing to that overall intrinsic clearance. So in that case, we automatically calculate the FM values for each of the enzymes. So again, you would be set up to go directly into the DDI module and run at least the steady state predictions utilizing the FM values for individual CYP enzymes, at least for these 5 enzymes for which we have the models. Of course, if you are importing the Km and Vmax values directly and not the intrinsic clearance, you always have an option to come directly to the DDI module, and the FM values are calculated automatically here from the K and Vmax values and the enzyme expression levels in gut and liver. And again, this is just one of the examples of imported structures. So you do have ability to now set up model with the import of the structure to do a complete model setup, accounting for PK. We set up for predictions of not only fraction absorbed anymore, but also the fraction bioavailable with some of these predicted or your experimental in vitro clearances. And if you are importing the predicted clearances, also going into the early predictions of DDIs, utilizing the predicted FM values. Some of the additional models that we also added into import structure feature are classification models. We don't have actual values or quantitative value on these properties, but knowing the likelihood of blood-brain penetration, or knowing the likelihood whether your compound would be a substrate or inhibitor of some of the transporters, can be also useful for you in terms of decision making for different projects. So even though we don't have quantitative values for this, we at least add a qualitative prediction. And at the bottom of the GastroPlus form in the notes field, you would see a note on whether your drug or your compound is likely to penetrate the blood-brain barrier, or whether it is likely to be a substrate or inhibitor for PGP or inhibitor for OATP. In terms of transporters, these are the ones that we have currently models for in ADMET Predictor, but our cheminformatics group is working really hard on adding new models, so the offering of predicted, at least classification models, will be expanding in the near future. The additional setting, you know that for quite some time now you had an option to include paracellular pathway in the absorption, in the intestinal absorption. So again, we've added this setting during your structure import, so you won't have to go through every single compound and tune that paracellular permeability on or off. Again, you are able to do that setting directly during the structure import and have all the compounds accounted for automatically. The default setting is on. If you prefer not to use it, you can just turn it off directly in this window. So that's briefly for the expansion of the ADMET Predictor module. Our next big improvement or big addition is the dermal model added to our additional dosage routes module. And again, we've made presentations and announcements on these modules a number of times. By now, everybody is probably aware of the fact that this was developed in collaboration with GSK. The main focus was on looking at the transdermal absorption. So looking at the topical administration of the compound on the surface of the skin and predicting how the drug is moving through the stratum corneum, through the viable epidermis, getting into the perfused layer, into the dermis, where the drug can get absorbed into systemic circulation. And also accounting for aspects like absorption through the hair or through the sebum surrounding the hair and so on. For the aspects on the surface of the skin, we did try to account also for some of the formulation aspects, which I will discuss a little bit more in detail in one of the subsequent slides. And this figure is just showing a schematics of the processes that we are accounting for, things like partitioning and diffusion directly through the layers of the skin, and drug getting into systemic circulation from dermis, but also possible absorption through the hair or through the sebum surrounding the hair, again, possibly getting into systemic circulation. When it comes to the dermal model, there are a few complications that we need to account for, one of them being large regional differences in the skin structure. And some of these would include the differences in the thicknesses of these individual layers. So it will change depending on whether you are applying your drug on face, arm, leg, back. So all of these needs to be accounted for. And the other aspect is also the blood flow. So again, depending on where the drug is being applied, the blood flow will be creating different sink, and will be getting the drug into the systemic circulation at different rates. We also tried to account for the skin ontogeny, for the development of the skin, which becomes a major factor, especially in the neonates and infants, and especially if you are dealing with the premature neonates where the structure is not formed well. And this picture is showing the embryonic, fetal, neonatal, and I think this one would be the mature neonates, which have already fully formed all layers of the skin. But for premature babies, you may need to consider higher permeability, as the barriers are not well formed yet. And we did account for it, for these aspects, by accounting for changing the skin thickness for individual regions of the skin for the application sites, but also especially for the neonates and premature neonates, we do have also a model accounting for modification in the permeability. As you can see, when we were doing a literature search, we found a apparent correlation between the transepidermal water loss in these young babies and the permeability coefficients for number of drugs. This one is showing only the lignocaine, but we've seen similar relationships for other drugs as well. So the permeabilities, the predicted permeabilities, are now getting automatically scaled to account for this increased permeability in the very young neonates. The window, the structure of the model is displayed here again. We are accounting for the possible pathway through the individual skin layers, as well as going through the sebum or the hair. And finally, the whole model is linked, of course, to our systemic circulation, where you can describe the distribution by either compartmental model or, again, having it linked to the full PBPK model. And when it comes to the physiologies, right now the program includes built-in default physiologies for human for number of different regions: arm, leg, abdomen, back, face, and scalp. We don't have any animal built-in physiologies yet, but just as with any other physiologies, you have an option to create custom physiology. We are, of course, working on trying to collect the information to describe the preclinical species as well, but if you need to do modeling in preclinical species immediately through these custom physiologies, you have an option to start doing that even before we have the built-in physiologies included. When it comes to formulations or formulation types that are available, we did try to follow the FDA classification for the formulations. for the formulation types, accounting for the liquid formulations, which could be simple solutions, suspensions, or emulsions, and also accounting for semi-solid formulations that would have larger proportions of the solid components, and again splitting these into gels, creams, ointments, or pastes, depending on the amount or fraction of solid, water, and the volatiles. We are classifying them into these 4 options. To make it a little bit simpler for you to choose, we actually did name the individual formulations, try to name them as closely as possible to these classifications, so you don't have to keep figuring out whether your formulation should be marked as a suspension or as an emulsion. We tried to mark them directly in the formulations. So the options that you have for transdermal dosage forms are the simple liquid solution, liquid suspension, which would be just a homogeneous solution of APR or a solid particles dispersed in the liquid solvent. We do have the semi-solid formulations, ointment and paste, lotion and gel and cream. And again, the difference between these is in their composition, in the fractions of the solid, water, volatile in that whole formulation. We do include also one of the controlled release formulations. We include a reservoir patch, which assumes an APR solution in a reservoir compartment on the top of the skin, where the rate limiting step is assumed to be the release of the drug from the reservoir, reservoir in the patch, and the drug that gets released is quickly absorbed into stratum corneum, and then the model takes over in terms of diffusion through individual skin layers and possibly getting into systemic circulation. For any of these transdermal dosage forms, of course, you need to define things like dose volume, application surface area, and application time, how long the formulation actually stays on the top of the skin. And of course, for some of these dosage forms, you need to specify additional parameters, things like particle size or particle size distribution for the formulations, including API as a solid dosage form. For emulsions, what is the proportion of the dispersed and continuous phase, and so on. And for reservoir patch, of course, you need to define a release profile, which, just like with our controlled release formulations for standard PO doses, could be defined as a tabulated or a Weibull function. And this is not really a transdermal dosage form, but we have included it along with the dermal module for the subcutaneous administration. And right now you will have an option to do a administration subcutaneous injection of a solution. And here the additional parameter is the effective depot volume, or a volume into which the injected solution initially distributes in the tissue. Very quickly through some of the formulation aspects that we are accounting for, especially for the transdermal dosage forms for the topical administration, evaporation of the vehicle, whether it is a solvent or a continuous phase in the emulsion formulations, is one of the important aspects, and we do include that in the model, so the model would be able to account for the evaporation of the vehicle, how it affects changing concentration gradients, and that subsequently affects the absorption of the API into the skin. And here we've included a number of built-in models for possible prediction of the evaporation rate of the vehicle. And you also have an option to define it as your own user-specified selection. So again, on the evaporation tab, you have an option to select from the predefined models, or if you have done a measurement for the evaporation rate of your solvent, you can simply define it in milligrams per second or percent per second or milliliters per second. For emulsions, the additional aspect that you would need to account for is how the drug is getting released from the droplet, from the dispersed phase into the continuous phase of the formulation. And for this one, we are providing two models, one assuming very fast equilibrium, very fast distribution between the continuous and dispersed phase, or diffusional model assuming a slow diffusion through the membrane surrounding the dispersed particles and the drug slowly getting into the continuous phase. And again, you would have option here to select from equilibrium or diffusional model, and you would need to define some additional parameters, either partition coefficient for the equilibrium model or the rate constant for the diffusional model for the slow kinetics. With any kind of emulsion, you of course need to define what is the volume fraction of the dispersed phase versus the continuous phase, and how the dispersed phase behaves in contact with the skin, whether it is showing a phobicity or whether it is not getting attached to the skin very well. So subsequently, once the drug gets into the skin, into the top layer of the skin, we need to account for the diffusion or distribution through individual skin layers. And two basic parameters that are important for getting the drug in between different skin layers and diffusing through each of these skin layers are drug diffusivity and partition coefficient. And again, we did not have enough data to build one QSAR type model for all of these diffusion coefficients and permeability or diffusivities or partition coefficients, but we have included from literature some of the more commonly utilized models to predict these parameters based on the drug properties. The common properties that are used in these equations are molecular weight, log P, log D. So these are included as a choice for different compartments. You would have up to 3 equations for each of those compartments for predicting the partition coefficients and diffusivities. If you have done in vitro measurements and deconvoluted or fitted your diffusivities and partition coefficients to your measurements of the permeabilities in Pleuthei-France cells, you have an option to define these exactly as a user-defined and simply enter the values that you obtained from analysis of your in vitro data. One important aspect to account for, especially for the skin layers, as these layers get relatively thick and it will take for the compound to diffuse through the skin layer, is to account for the kinetics of diffusion through that skin layer. Right? So if we accounted only for differences in partitioning between individual skin layers as driven by different composition of those layers, we'd end up with sort of an equilibrium, instant equilibrium type model, and the drug quickly appearing in the systemic circulation. The situation, however, is a bit different, where at the interfaces between the layers you would see this kind of jump or concentration difference due to partitioning coefficient, but then you would also see a gradient across the skin layer as the drug is slowly making its way from the top of that skin layer to the bottom of the skin layer before it partitions into the next skin layer. So to account for this diffusivity or this time for the drug to get through that skin layer, we opted for splitting each compartment into a number of sublayers. Each of these sublayers for given skin layer have the same properties, but it allows us to, this discretization does allow us to account for the concentration gradient along the entire skin layer. And where it is important is it really does help to a model or to account for that initial lag in the appearance in systemic circulation that you might see with the transdermal formulation, because of the time it takes to diffuse through all of those non-perfused layers before the drug reaches the veins in the dermis. So as for model inputs, again, the same as with many other models, you need to define the physiology. And as I mentioned, for human, we have built-in physiologies. For animal species, we are working on those. And in the meantime, you have the option of using user-defined physiologies and define these for any animal you may need to model. Formulation and administration, again, the basic parameters would be the dose volume, application area, application time, and any additional parameters that would be relevant for a specific formulation or dosage type that you are trying to administer. And the last set of parameters, again, are the tissue partitioning and diffusion coefficients, which determine how quickly the drug is getting through all the skin layers, or whether it accumulates in any of the skin layers more, which again slows down the appearance in the systemic circulation. Some of the examples, and just very briefly, many of you probably saw examples of clindamycin that was presented at the AAPS last year by a couple of nice posters prepared by Anu doing a presentation or prediction of different formulations for clindamycin on different administration times, single dose as well as multiple dose, and you can see all of those worked out very nicely. Similar prediction was done for tazarotene. I'm not showing that one in here. Another example for different type of administration for the dermal patch, where we found the data in literature for vopindolol, where the patch was applied to the skin for different times, or different size of the patch was applied. So what we've done, we fitted a viable function for the release of the drug from this patch formulation against one of these studies, and I believe it was this one, a 7-day study for applying a 20 centimeter squared 14 milligram patch, and use that to predict how the exposure in the systemic circulation would change if the same size of patch was applied for different days, or for different duration, for 1 day, 3.5 days, or 7 days, or if the patch size was changing. So if we cut it in half, or if we increase the size, how much it would change the exposure. And you can see it translated fairly well for this example. Just a brief example on the additional administration route that we included with the dermal module is the subcutaneous injection. And again, everyone's favorite compound, midazolam, where we found the data from literature from a study, crossover study, where the midazolam was administered IV and subcutaneous administration. You all know that midazolam is one of the default models in many of our applications. So we use the IV data to basically just validate that the model that we have, or that we commonly use, is well applicable to the population of subjects also used in this study. And then we use that to predict the subcutaneous administration of midazolam. The one change that we've made here was abdominal subcutaneous tissue blood flow, where again we found in the literature that for non-obese subjects, the blood flow in the abdominal subcutaneous tissue is actually higher in fasted state than in fat state. And that accounts for fairly high or fairly fast absorption of the drug from that subcutaneous fat into the systemic circulation. We do have still a little bit of mismatch here, which could be manipulated by slight decrease in adipose Kp. And this was just to point out that the IV dose has not changed a whole lot by changing this Kp. So by administering to IV, that application was not as sensitive to the adipose Kp, but for starting from the adipose, it does become more sensitive to that partition coefficient. So this could potentially be another way of determining the adipose Kp values, the adipose partition coefficients, without having to do the measurements or sampling the adipose tissue. Just by utilizing subcutaneous injections could give us a better idea about that partition coefficient as well. Going into the oral cavity module, and this one, again, many of you have probably seen that this one was also developed in collaboration with a company. This time it was Merck, who gave us a lot of help on developing the module and giving us scientific feedback. You will see a lot of similarities between the dermal and oral cavity dosing. Actually, one aspect is we have several different skin layers that the drug needs to diffuse. It needs to get through the epithelium before it reaches the perfused layer of lamina propria, from where it can get into the systemic circulation. And again, we are dealing also with some regional dependencies in the mouth, even though maybe on the smaller scale than in the skin, But again, we have differences in the thicknesses of these areas, in the blood flows through the perfused layers, and so on, which we needed to account for. In addition, we also are dealing with the saliva flow throughout the oral cavity, which is also distributing or redistributing the drug from the original administration site and swallowing lands the drug in the stomach. So we have the combination of intestinal absorption as well. The window looks very similar to the one that you would see for any of our other additional dosage routes. Of course, the layout of the model will be slightly different. We have the compartments representing individual regions of the oral cavity, and from each of these regions, the drug can, of course, get into the systemic circulation. And again, you can describe that distribution with compartmental or with a PBPK model. The additional aspect that we need to account for here and is marked by these orange arrows is the saliva flow and how that will affect the drug distribution in the saliva in the oral cavity before it gets absorbed. And again, for the physiologies, we did try to include some built-in physiologies. For oral cavity, we have built-in physiologies for human, again, with age-dependent changes, especially in surface area thicknesses and so on. But we also have built-in physiologies for few preclinical species. And for this one, we were so far able to build physiologies for dog, monkey, and rabbit. And again, you have ability to create custom physiologies. So if you need to do administration for animal species, which we don't include yet, you could possibly create your own physiology for that species. Just like with any other modules, just double-clicking on any of those compartments brings up the compartment with the specifications, with the physiological parameters relevant for that compartment. And the major parameters would be, of course, absorptive surface area for each of those regions, thickness of the top layer, epithelium layer, as well as the thickness of the bottom perfused layer, lamina propria, which is the one from which the drug gets into the systemic circulation. For some of the regions, for sublingual region, we also have a maximum volume of the saliva that can be held there. For each region, we have the blood flow rate. For buccal and sublingual, also saliva production rate, and so on. So these are all parts of the built-in physiologies. For the dosage forms, you have basically three options: administration of solution, administration of a tablet, or controlled release formulation, buccal patch. So for buccal patch, clearly that's administered in the cheek, and as an input you would need to define the release profile either as a tabulated or a viable function. For these others, we just made it a little bit more. Again, they are only solutions or a simple immediate release tablet, but we did define or predefine some of the common administration sites like sublingual or lingual, top of the tongue, just to make it faster for you to set up the application site or administration site. But we did keep also a generic form of solution or a tablet where you can define exactly into which region of the oral cavity you are applying it, and you can have any combination of the application sites. So for the application site, you would define what portion of the dose was administered in each of these different regions of the oral cavity. And with buccal patch, of course, it goes into the cheek, but you would again apply or specify the surface area of the patch, determining the surface area for the absorption directly from the patch into the oral mucosa. And just like with any other module, the application site is highlighted in green just to give you a better visual indication as to where the drug is initially starting from. For the experimental settings, you can define the exact study design. So things like, did you ask the subjects to not swallow for a certain period of time? If you allow them normal swallowing, did you give them glass of water after that hold period, after not swallowing, to wash the remaining drug back down into the stomach, and so on. So we try to account for all of the common types of study designs to account for the drug movement, especially when it comes to the saliva production, saliva flow, and swallowing. So you can set up any of those designs and define corresponding parameters related to the selected design. When it comes to drug-dependent properties, there are really just the three major properties that need to be defined, and this would be partition coefficients or fraction unbound in the mucosa tissue, drug diffusivity through soft tissues, and drug diffusivity through keratinized epithelium, where the keratinized epithelium represents the epithelium or the top layer of the palate and the gingiva. All the other tissues are assumed to be soft tissues and would have a different diffusion coefficient, or could potentially have different diffusion coefficient. And here, these parameters, again, similar to the dermal dosage forms, this could be obtained from your in vitro experiments in France cells or any other diffusion experiments through the tissue slices. And that's what we did when coming up with default relationships for predicting these partition coefficients and the diffusivities. We had data from in vitro measurements for 9 compounds, which we were able to analyze in terms of what would be the diffusivity through that tissue slice, and what would be the partitioning between the aqueous layer and the tissue. And we were able to find a simple relationship between these two parameters and log D for 7.4. And these relationships are built in as the default models for predicting these parameters based on the properties of the compound. So when you first select to set up the model for the oral cavity, those relationships are automatically utilized to predict your fraction unbound in tissue and the diffusivity through the soft tissue. And again, for the case studies, there was a presentation by Wim Feng, prepared a nice poster describing the model, describing the predictive capabilities for a couple of compounds, again, at last AAPS. And this was already also turned into a full publication, which just came out officially this month, but I think the early views were about a month ago. So you are welcome to go and see this publication, get the details of the model as well as the validation cases. For the biologics module, again, as many of you know, we've been working on adding the PBPK model for large molecules, and currently, the first implementation is really focused on the processes for monoclonal antibodies. And the processes that we include are the standard processes relevant for the PK of monoclonal antibodies, lymphatic diffusion, lymphatic distribution, the convective flow through the pores in the epithelial cells, fluid phase endocytosis, so drug getting through the endocytosis, ending up in the endosomes from the plasma space or the interstitial space, FcRn binding as a protective mechanism against degradation in the endosomes, and also a target-mediated distribution and clearance. And the relevant dosage forms that we included for now for monoclonal antibodies are, of course, the intravenous administration, but we have also added a subcutaneous administration route as well. So you have the major routes for the monoclonal antibodies too. For the lymphatic distribution, again, it's added to our PBPK model, and this is actually something that you might turn on also for small molecules, so it's more of a generic feature that you can account for now for small molecules or the antibodies. It is, of course, required for the antibodies. For small molecules, it may be relevant for some of the more lipophilic molecules, and you may explore this process. I will not be going much into details of these individual models. A lot of the models that we are using for all of these basic processes are based off of the work of Joe Baltazar's lab from Buffalo University. So for the transport, just very briefly, for the convective transport through the pores in the epithelial cells, as well as for drug getting into the lymph from the interstitial space, the major parameter that we are utilizing is the reflection coefficient, which basically determines the resistance of the pores to the drug diffusion through those barriers. And here perhaps the one comment worth to point out is when we were doing evaluation for distribution in different tissues, we did notice that the drug would be distributing at the different rates, or the antibodies would be distributing at different rates or to different extent into different tissues. And this would be, or we assigned this aspect, the rates of distribution or the rates of flow between the plasma and the interstitial space through the pores to the leakage of the tissue. So the model does include as one of the physiological parameters what we call a leakage parameter that allows us to define how leaky or how big or what is the fraction of the antibody that could be actually flowing through those tissues. And as you would expect, brain is considered to be one of the tighter tissues, so there would be less uptake through this convective flow. Some of the tissues like kidney or liver seem to be more leaky, and there would be more of a convective flow through those tissues. So that helped us to distinguish the differences in the uptake in different tissues via convective flow. The built-in parameters, of course, include the physiological parameters for the lymph flow for each of the tissues, as well as default parameters for these reflection coefficients, which would be more or less constant across variety of IgGs, and we do have built-in parameters specific for human and for mouse right now, based on the validation of several antibodies distributing in human and in mouse. For fluid phase endocytosis, again, modeling it via rate, defining the rate of endosomal uptake from the vascular space or from interstitial space, and subsequently recycling of the endosomes back into the surface of the cell, either on the plasma side or on the tissue side into interstitial space. And along with this, of course, comes the process of FcRn binding, where the drug, as the endosome forms, the pH is changing in the endosomes that would be leading to the degradation of the antibody, but the antibody which is bound to the FcRn receptor will be protected and will be released back to the either plasma or to interstitial space, and as the endosomes recycles back to the surface of the cell and the pH changes. So the model does include the transition of the endosome from the pH 7.4 when it's being initially formed on the surface of the cell through the early endosome at pH 6 and back to recycling to the surface of the cell and returning to pH 7.4. And the model does include different on and off rates for the antibody at these different pHs. So would be more tightly bound at the pH 6 in the endosome, and the drug will get released. There is less binding at the high pH, and the drug gets released once the endosomes return to the surface of the cell. And again, the physiological parameters relevant to this, FcRn concentrations and as well as endosomal volume are included as part of the physiologies. And for the more drug-dependent properties, things like endosomal uptake, recycle rates, on and off rates, which again, we would consider them to be constant across IgGs. These are as part of built-in set of default parameters, and again, we have these specific for human and for the mouse. And finally, the last process incorporated is the target-mediated disposition for the antibodies. Right now, this one is limited to the cell surface-bound antigens, so we are not incorporating yet the soluble targets that would be distributing with the complex with the antibody throughout the system. What we include right now is the receptors or antigens that are bound to the surface of the cells, and once the antibody reaches that tissue, it can bind to the antigen. The bound antibody would be internalized and degraded along with the antigen as the complex. So the parameters to define for the target-mediated disposition, of course, is the expression level of the antigen in given tissue, as well as the binding parameters, the on and off rates for the antibody binding and dissociation with the antigen or with the receptor. And we've tried to make this as similar to the small molecule setting as we could, just to make it easier for you to, for those who are used to using GastroPlus for small molecules, to make it more intuitive in terms of setup. So for each of the tissues, when you are dealing with the antibodies, you would have additional tab where, similar to what you are used to doing with enzymes and transporters, even for antigens, you could define the expression level of the antigen and degradation rate of the antigen, molecular weight. And then you would have, similar to enzyme or transporter table, where you are used to defining your Km and Vmax values for the interaction of your small molecule with enzymes or transporters. For large molecule, you would have an antigen table, where again you would be defining the interaction parameters, the on and off rates, for interaction of your antibody with the specific antigen in individual tissues. For, as I mentioned, we do include also the subcutaneous administration for the antibodies, and here the additional parameters, of course, would be the tissue compositions in terms of the interstitial space volume, blood flow through the subcutaneous space, lymph flow through the subcutaneous space, and another parameter, again, the effective depot volume, which is an important parameter for both small molecules or large molecules with the subcutaneous administration, which again represents the tissue, volume of the tissue in which the initial injection distributes, the initial administration or the administered volume distributes through the tissue. Some of the case studies, this one is showing the effects of FcRn binding and utilizing just the default parameters that we ended up with for IgG. This was for the distribution in mouse, showing the effect of FcRn binding on the antibody systemic circulation. With FcRn binding, we had a nice match. With removing FcRn binding, so we set the binding constants to 0, the elimination of the antibody was quite a bit faster. And again, this used all default parameters for the mouse, and the same parameters worked for a number of different IgGs in the mouse simulations. Similarly, again, IgG1, we had an example where this was administered in control mice, and in mice with the xenograft tumor, so we were able to incorporate binding to a specific antigen present in that tumor. So the top row with just the simple FcRn binding is using the same exact default parameters as you would see in this example with FcRn binding. The study was again done in mouse, so the same default parameters for the reflection coefficients, FcRn binding, were used for both studies, and as you can see, it nicely demonstrated or nicely accounted for all of the doses. And finally, to account for the mice with the xenograft tumor, we expanded the model by adding a tumor tissue to the PBPK model, defined the on-off rates and the tumor expression level, and modeled the dose dependency again of the antibody when administered at different doses into this physiology. And for an example of subcutaneous injection, this is again an IgG, but in this case it was administered in human. So a nice demonstration of how well the default parameters for the standard distribution in terms of convective flow, endocytosis, FcRn binding, and the degradation in the endosomes works, how the human default parameters work. We had this data for this antibody at different dose levels, and as you can see, those default parameters nicely accounted for the IV administration or the distribution. So we then use the same set of parameters to model administration of that antibody by subcutaneous injection. And this was an infusion, or a very short infusion, subcutaneous infusion. I think the total volume was about 1 milliliter, but accounting or assuming that the initial dose volume distributes only to the extracellular tissue volume, it would actually distribute into quite large volume of the tissue initially. And this was one fitted parameter that we had to account for, that initial depot volume, which ended up being 60 milliliters, and accounted for distribution for all of these 3 doses with the subcutaneous administration. Very briefly, through the new models that we advertised that we would be adding for the DDI standards database. We've already discussed earlier that we were planning on adding the rifampicin model, which was something that the work was done actually by group at Roche, and they did a nice publication of creating rifampicin model in GastroPlus and validating that model against for predictions of DDI with midazolam. So that model, which is included in GastroPlus, is really based on that publication by Guillaume. We have worked over the last few months on incorporating itraconazole model, and the model that we ended up with does include all the major metabolites. So we have itraconazole as well as 3 of its metabolites, and accounting for the inhibitory effects of all of these compounds on the 3A4 activity. As we were doing the validations, one of the compounds for which we had the DDI data with these compounds and were using them in validations was triazolam. So you now have additional 3A4 substrate triazolam also in the database of standards. Just a brief view of the performance of the itraconazole model that we have. This was showing the performance from 9 different studies, 9 different published studies, where the application or the administration of itraconazole and midazolam varied. So different doses of itraconazole, different doses of midazolam, different administration strategies in terms of when midazolam was taken, after itraconazole, after how many doses, or with 2 or 4 hour delay after itraconazole administration. And there were also differences in the study protocol in terms of the meal times. And that is one of the critical aspects when predicting the itraconazole DDI. It is something that you will need to pay attention when using this model. Make sure that you correctly define your fasted or fed state, or how the subject, or when the itraconazole versus your substrate compound is given, because itraconazole, being a low solubility compound, is heavily affected by the fed or fasted state, and that will have significant effect on the prediction of the itraconazole PK and subsequently DDI. And that turned out to be a critical aspect in getting a good prediction across all of these studies, to have an accurate account for the meal times and how those were given with respect to itraconazole and to midazolam administrations. And finally, just a few brief comments on the licensing. Again, something that we advertised already, and those of you who have some of our other softwares, ADMET Predictor or Medchem Studio, notice that we started doing a switch into this new licensing system, FlexNet Manager from Flexera server or from Flex software. Sorry. It is a license server-based license system. Many companies may already have this system in place, so for those companies, it's going to be very easy update, where you would just need to add our system into the into that server. It simplifies the unlocking process in terms that you no longer need to set up a time with our offices. All of the unlocking can be done over email, where you will send us information. We'll send you back the license file that you would import into the system. It does make a little bit more complex installation if the system is not in place yet, but hopefully, as that's one-time aspect, and once it's installed, it becomes a very easy and user-friendly handling. Hopefully you will appreciate the changes in the licensing system as well. For those of you who've ran into the common issues with the computer ID changing on you when you plug in your computer at home or at work, this should no longer be issues. So a lot of headaches should be solved by using this system. And finally, just to give a credit to everyone who contributed to this version. Of course, we have a great group of people within the simulation technologies team that is mainly working on the development of GastroPlus. Jim, Haing, Kay, and Jessica all have done a great job in trying to bring this version to life. Of course, we can't forget Ray. Many of you knew him from his days at Simulations Plus. He's currently at Allergan, but while he was here, he did a lot of work and made a big contribution to the development of especially our dermal module. As I mentioned, the dermal and oral cavity modules were developed in collaborations with companies, the dermal module with GSK and Stiefel, and the oral cavity module with Merck. So we need to thank to all of the scientists from these teams who helped us with their feedback and a lot of testing and validation for us as well. Mike Bolger, our chief scientist, and also the other teams at Simulations Plus that helped in supporting roles with the development of GastroPlus. And with that, that concludes the presentation, and we'd be happy to entertain any questions if there are any.
Thank you so much, Vera, for the really excellent and insightful presentation. Once again, if you'd like to ask a question using your telephone, please use the hand-raising icon on your control panel and be sure to enter your unique audio PIN. There have been some questions, written questions that have been submitted, and so we'll start with the first. This is related to the subcutaneous administration. How should the input parameter, effective administration volume, be determined?
Yeah, that is a very good question, and we've tried to research this, and we found some publications suggesting models on what this effective depot volume would be, but so far we have not really come up with a good way of scaling your dose volume to what kind of effective depot volume it would actually translate for any kind of formulation or a drug. All we were able to set up for now is the minimum depot volume, assuming that the injection distributes only to the extracellular space. There is going to be a minimum tissue volume that will be affected by that initial injection based on the injected volume. But beyond that, so far we ended up fitting that initial depot volume. For midazolam, for the subcutaneous injection that I was showing, it actually turned out to be that minimum depot volume. So that one we estimated by simply assuming that your injection volume, which I think was 1 milliliter in that study, would distribute only to the extracellular space. So by knowing the fraction of extracellular space, we determined what tissue volume would be affected, and that was a correct estimate. For the antibody, the volume ended up being a bit higher. So at the moment, it is a more of a fitted parameter, but we are researching this a little bit further to see if we can come up with a more predictive model based on your administration volume, figure out or predict what would be the depot volume.
Thank you, Vera. Another question, can you discuss or comment on the source or amount of data that was used to train the CYP enzyme kinetic models? Also, have you done any validation of predicting absorption or bioavailability from chemical structure? And if so, what accuracy were you able to achieve?
So for the size of data sets for those 5 CYP enzymes, that would be a better question for our cheminformatics groups. But if I remember this correctly, the data sets were about 100 compounds for each of the CYP enzymes give or take few compounds. I think they might be a little bit over 100 compounds for each of those CYP enzymes. When it comes to the accuracy, we've done this, and this is something that anybody with the access to the ADMET predictor module with the metabolism predictions can do on your own. With the 21 set data set, our SDF file that is included with your tutorials, it came up to about 70% of the compounds were predicted within twofold. The bioavailability error was within twofold. One of our scientists in the cheminformatics group was also doing a more thorough evaluation on the larger data set, and I think he had 60 compounds, and that came up with about the same statistics. Around 60 to 70% of the compounds were predicted, had bioavailability predicted within twofold error.
Thank you, Vera. Another question, with the dermal model, there are a number of options provided for the estimation of the diffusivity's partition coefficients. Is there a method that Simulations Plus recommends using for early predictions based upon the type of the compound? For example, acid or base, hydrophilic or lipophilic, etc.
No, unfortunately, we don't have that kind of recommendation yet. There wasn't, we haven't processed nearly enough compounds through this model yet to be able to give this kind of recommendation as to which method works best. From the examples that we worked with, the default model worked with some of the examples, the one that we set up as a default, the when casting Nietzsche model, but for example, for Vopindolor, for the compound that we modeled with the transdermal patch, we had to use different model to account for the distribution through the skin tissue. So hopefully as we go and as we are utilizing this model and getting feedback also from our users, we will be able to come up with these kinds of recommendations in the future. But at the moment, there just wasn't enough data yet to make that kind of recommendation.
Thank you, Vera. Another question, and this is related to the dermal model as well. What are the default number of sublayers that are defined for the different skin compartments?
I think we ended up defaulting to 10 sublayers for stratum corneum and 5 sublayers for the remaining, for the viable epidermis and for the dermis.
Okay, thank you, Vera. Another question for biologics. Do the human physiological parameters scale based on age? That is, are there differences between pediatric and adult groups?
For the biologics, no. We were not able to get that kind of data yet to scale those biologic-specific parameters like reflection coefficients or endocytosis rates and so on between the adults and pediatrics. So for now, it would be based on the data in adults, but we don't have pediatric data for those yet.
Okay, thank you, Vera. I don't see any other questions. And so with that, we will officially conclude today's webinar. Thank you again, Vera, for the really nice discussion and presentation. If anyone on the call today missed any part of today's presentation, the playback will be available at our website, www.simulations-plus.com. And also, upon request, the presentation slides can be made available and shared with colleagues. Thanks again, everyone, for joining us, and have a wonderful day. Bye-bye.